All right, so chapter 10, we're going to be looking at graphs specifically today, section 10.1 in this video. Might go into 10.2, I haven't decided. The idea of a graph is you're going to have some endpoints. And they're going to be connected with edges. And you typically label the endpoints. Okay, so this edge here, you can see that it makes A and D, what we'd call them adjacent. So A is adjacent to B and D because there's a one path between A and D. There's a one edge between them. It's not adjacent to C, so it'd take two flights, if you will, to get there. We would say that E is isolated. Okay, so obviously D is adjacent to, well, C and A. B is adjacent to C and A. And who are we missing? C, B, and D, right? That makes sense. Again, adjacent, one path between them. Okay? We'd call this a loop. And therefore, D would be adjacent to itself. That's kind of weird, but it's true. Well, we'd say that these lines here, this one and this one, are what we'd refer to as parallel edges. Not parallel in and of themselves, but parallel, because they're like, they never touch or whatever. The idea is they go to the same place. They go from the same endpoint to the same endpoint. So there you go. Very similar to a highway and the maybe the what do you call it? The side road that runs alongside the highway, the access road or whatever. It's a similar situation there. Okay, they don't have to be running side by side. You could you can go to Newburgh from Beaverton, like Shoals Ferry to 219 and whatever that away, or you could go down. You can go down to Tiger, go out 99W or whatever, and you get to the same place. They're not even remotely what you would consider parallel. They just go from the same place to the same place. Okay. Not exactly the greatest deal because the 99W doesn't go through Beaverton per se, so you'd have to go down 217 and then hit it, but that's the idea. Okay. We'll look at some graphs are like this one here. Some graphs are more like this guy. This is what you would see if you typed into Giggle and you're like, hey, how do I get from hither to yon? All right, cool. So I need to go from Portland to Baker City to Bend to Corvallis, or I don't know, where would this be? I guess Lincoln City or something. It's a circuitous route to get to Lincoln City from Portland, but whatevs. It'll work. It's fine. But the idea is the directed graph means, or sometimes referred to as a digraph, show an order to it. All right, from here to there to here to down to here, back over to Lincoln City. Obviously can be done in the case of laying out your trip that you're going on. It can be obviously seen if you're out delivering packages or things of that nature, clearly. Okay. Could also do you could talk about in terms of a project, right? So whenever you think about doing a project, and we will look at using these for projects later, is the idea of when it comes to scheduling. Okay, obviously, I'm going to paint the bedroom. Are you? Okay, cool. Well, you probably got to move the furniture out of the way first, get the stuff out of the bedroom, whatever. You better tape if you're going to do that, and so on and so on and so on. There's a million things to do before you get to the actual painting process, and it kind of matters what order it comes in. Some things it doesn't matter. Like, okay, I'm gonna pull the switch covers off the wall first. Okay, well, good. Okay, I mean, I feel like you could have pulled the bed out first. You're right; those are probably interchangeable. And so there's just things that obviously there's some things you have to do prior to other things. That is the purpose of a diagraph. Right? Clearly, when you're running errands and stuff, it's going to matter one way or the other. When you look at Twitter and Facebook and things, and I don't have any of that crap, so I'll just pretend this is you. You have all these people down here that maybe are your friends, okay? So, like, you can talk about tracing someone. You know, someone is a friend of yours, and then they trace it down, and this person's got a million friends, whatever. It's a very similar procedure. You can go either direction on that, but in terms of, like, if you want to trace from one thing all the way down to the end. A girl at school was telling me the day I saw her, and she was talking about this one guy, and got kind of a creepy situation where she's like, he followed me on Instaface or whatever, but we don't have anybody in common. And I said, oh, that's kind of weird. So, like, she was trying to figure out how did he connect with her without actually straight up stalking her, and there really is no good way to find that out. Why? Well, so a complete graph works like this. This is just a few definitions that a person needs before you get carried away. A complete graph is where every point is adjacent to every other point, or if you will, every point is connected to every point. Clearly that one is so. This one is a connected graph, but there's only just the 3 lines because obviously everyone's connected. Everyone's adjacent at that point. If you're going to have 6, 6 is kind of a bear. Well, that's 5, I guess. Let's do 6. 6 is kind of a bear. If it's me, I give it one of these numbers first, obviously. Then let's connect from here. Why didn't you go across? Because I didn't feel like it. So 2, 3, 4, cool. By the way, there's 6. There should be 5 lines coming off of each of them. Is that correct? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and so on and so on and so on. Nice. Interestingly enough, there is a formula that says for a complete graph there are, let's figure it out. This is 3, 2, 3, 4, 5, 6. Here there are, if you count them, I believe there are 15. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on and so on and so on. Okay? So where are those coming from, Jay? Well, it's a good question. Turns out that this is something like 3 factorial divided by 2. This is 4 factorial divided by 2. No, 24 divided by 2 is not 12. Oh, wait, no. Hold on. No, I know what I mean. Not factorial, stupid ass. It's 3 choose 2. 3 choose 2. And this is 4 choose 2. Is that right? 4 choose 2 is 6. That's correct. What is 6? 6 choose 2. Let's find out. That's 6 factorial divided by 6 minus 2 factorial times 2 factorial. So that would be 5, 4, 3, 2, 1 divided by 4, 3, 2, 1, 2, 1. 3 times 5 is 15. Yep, that's exactly how it works. I had to think about that for a minute. Okay. Yeah. So there's 6 points, choosing 2 at a time. There's 15 ways to do that. The idea being is it doesn't matter which direction you're going because you're just saying it's an edge that connects 2 points. Okay. That's just a cute little thing, you know. You might really impress somebody sometime. You know, you're like, all right, cool, man. Something that also is interesting to talk about is, I'm going to start with this nice little complete graph here. Nice. So the question might become, what is the degree of each vertex or end? Okay. The question is, how many edges come into it? 3, 3, 3, 3. Cool. So then the total degrees, of course, would be total degree would be equal to 12. Hey, what is 12? 12 is 2 times the number of edges. That makes sense? Well, I would hope so, because each edge has 2 end points. So, yeah, there were 6 edges. 6 times 2 is 12. That will always be true. Something that we'll consider is this. Some of these are going to be odd. Okay, some Now look, I fixed it. This one is now 4. This one is now 1. Some of them will be odd, and sometimes some will be even. Sometimes they can be all even, sometimes they can be all odd. They can't. Yeah, they can all be odd. You have to be careful. There's a little caveat there. Yeah, it's kind of a fun deal. Not very hard to do. Just a matter of looking at it. What would happen if you had a loop? If you had a loop, okay, that's an edge. Each edge has 2 endpoints, and this guy now has 5. So you have 5, 3, 8, and 11, and 15, and 16. Wait, will the total number of edges, will the total degree always be odd? Even rather? Yeah, I hope so, because it's 2 times the number of edges, correct? Pretty easy to do. That's why I kind of really like this kind of stuff here. It's kind of fun. Nice. That idea that it's 2 times the number of edges, that's also known as the handshake theorem. That's how your book defines it. I've heard it called other things too. It's not really a big deal. Just be aware of that. Again, when you look at this, there can never be an odd number of odd vertexes in a graph of any kind. Doesn't really matter what it looks like. I'm going to connect these guys. Some of them I'm not going to connect back to each other, anyways. So here you go. This is 1, 2, 2, 1, 2, 3, 4, 5, 2, 2. Look at that. As promised, 5 plus 1 is 6. Everybody else is even. So evens plus evens plus evens is all evens. There will always be an even number of odd vertices, or 0 of them. Always, 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 always. Okay? Now, bear in mind that if someone gives you some information, how you draw it and how I draw it might be 2 different things. So here's the vertex. Here's who it's adjacent to. Okay. So, probably did this right. Before I assign a problem like this, I would just, here, let's go to work, see what happens here. I may have missed a couple. Let's see what happens. So, A, B, C, D, E, F, G, H. So, A, B, C, D, E, F, G, H. So, A and B, A and E. Cool. B is to A. Yep, I got that. C is to B and A. Now, the fact that C goes to A means I should have had a C here, and I didn't include that, and I feel awful about that. And ditto, I should have had a C here. I feel awful about that, so I'm just going to go with it. Oh my gosh, it's like a heart or something. No, a dolphin. It's a dolphin, isn't it? Anyway, whatever. E, notice that A and E, I got that part right, but then I got E goes to H. And H, and it goes to C, which means there should have been an H here. No, I'm not an H, you dumbass. An E, rather. So C goes to E, or E goes to C, yep. And then E goes to D. Now, the fact that I didn't have that connected here is kind of annoying. There should have been a D here as well. And then E goes to A. I already had that drawn in. That's cool. Now, what about F? F goes to F. Interesting. What does that mean? Well, it means there's a loop. Cool. It also goes to H. Now, that's nice. And it also goes to C. Now, the fact that F goes to C, C also has to go to F. So, again, oops. What happened? No. Okay. And H goes to F and E. That's right. Okay, cool. And then G, of course, is isolated. Now let's see if that's true. Does that make sense? So A goes to B and E and C. Cool. And B goes to A and C. Nice. And then C goes to B, A, F, and E. Yep. And D goes to... What happened there? Something's a little screwy. D. The way I've got D drawn up, only E goes to it. I guess we'll go with that. Cool. Oh, I see what I did. I put part of E on it. There we go. Cool. And then H, C. H goes to... Oh, no. So F goes to F. F goes to H. F goes to C. Yep. And then A, F. Yep, that's right. So you may have drawn that out differently than me. They are equivalent if they have the same relationships. If the same ones are adjacent to each other, if the same ones are connected, they are equivalent. It doesn't have to be the exact same looking. It's how the relationships exist. That's an important deal. Okay? It's an important thought process. So when you draw yours up, obviously I'll have to draw mine, and we may or we may not agree on what they look like, but we will agree on the relationships. Okay? All right, let's try this one here. Let's draw a graph with 4 vertices. They have degree 1, 2, 3, and 4. Okay, those are the degrees of each of the vertices. Cool, let's find out. Awesome. Okay, cool. Well, A, I'm going to draw him as if he has 1 vertex. Cool. B, he's going to have 2. Nice. Okay. And you're like, well, what about C then? C needs to have 3 and D has to have 4. Oh, can I try this? Yeah, I think so. Let's try. So now C has how many right now? C has 2 now. I need to have 3. So then, all right, now I give it 3. Awesome. Now how many does D have? D has 2. It needs 4. I can't connect it to one of these guys because that would mess him up or him up. Not cool. Can't go back to C because it'd mess it up. What if I just did this? Nice! 4 degrees. Okay? So you'll be looking at some of those. It's pretty easy to do and look at them that way. Not a whole lot to it. This is not a lot to it. It's just getting comfortable with them. It's somewhat fun, I think. Now, we are gonna do 10, 2 together at the same time. Okay, and we're gonna talk in this one about trails, paths, and circuits. Circuits being probably the most obvious of the bunch, the most important way to do it. I remember when I was a kid, it was very annoying to me. They just gave us this problem, and it just kind of pissed me off. And I didn't understand what was the big deal. Okay, and to this day, the way it was presented still just annoys the bejesus out of me. Okay, it's called the Bridges of Knigsberg problem. There's a town in, I think it's present day. I think it's in Poland now. I don't know. It used to be in part of Prussia back in the day, which is part of Germany, whatever. There's 2 islands. There's a river. Then there's 7 bridges. And the question was, could you start over here, cross all the bridges, and get back to where you started from? Or start here and get back to where or start there, or whatever. And the answer is hard to see until you looked at it like this. Let's look at A, that is the north side of the river, is a point. One of the islands is a point. One of the other islands is a point, and B is the south side down here is a point. So you've got 1, 2, 3, 4, 5, 6, 7 edges. There they are. What you'll notice is there's 3. The degree is 3 there. The degree is 3 here. The degree is 3 here. The degree is 5 here. And what you'll find is that no matter what you do, and we were never told how to do this properly. We were never like, I wonder why that works or it doesn't work. And it used to just annoy the bejesus out of me. Okay? And it turns out that it's the fact that we have odd vertices says that you cannot start at any one of them and get back to where you started from. It's not possible at all. So I'd like to demonstrate that with a nice easy graph that is similar but of course different. They're all connected, yes? Now let's say that I started here. Can I finish back here? You're like, well, no, dummy, of course you can't. And you're absolutely right, because I can't come back without backtracking. That, when I say can't get back without backtracking, it's not doable. It's not possible. Okay, so you're like, well, what if I connect these guys? Well, that's a good question. So now that I've connected them, now if you look, they're now all 2, 2, 4, 2. They're all even. And what you'll find is, no matter where you start, let's say I start here, 1, 2, 3, 4, 5. I can always get back to where I started from if they're all even. If one of them is odd, if only one of them is odd, if one of them is odd, then 2 of them are odd. Does that make sense? Okay. So if one of them is odd, 2 of them are odd. This one here is also odd. When there are exactly 2 odd vertices, you can start at one odd and finish at the other odd without backtracking. So I go 1, 2, 3, 4, back to here, and then I'm back to this guy. Or I could start here and go 1, 2, 3, 4, and finish at that guy. I can always do that without backtracking. Start at one odd, finish at the other odd. If you start anywhere else, what will end up happening is this. Let's say you start here. Cool. Down, up, back. Now I'm screwed. And you will finish. You'll end up finishing it at odd every time. So if you have exactly 2 odds, then you can start at one odd, finish at the other without backtracking. If there's more than 2 odds, then you're stuck. No matter what you do, you're going to end up backtracking. And if they're all even, like this, 1, 2, 3, 4. It doesn't matter where you start. You can always get back to where you started from without backtracking. Okay, that is a theorem. Okay, we're going to talk some more about that in a few minutes. Now, some definitions. So, a walk from V to W is it represents a walk from V to W will be set out something along this line. So let me just put up something here real quick for you. Here's my little graph. Here's V, here's W. And your book does this: edge 1, edge 2, edge 3. Well, why'd you write it? It's not edge squared, you jackass. Cool. And so, this is B, C, D, or what have you. So if I wanted to go, I would go V. Your book writes it like this: E1, B, E2, C. And then you can go crazy. I want to go E5, D, E6, W. That would be a walk. Okay? It'd be a trivial walk if you just started at V and ended at V. Okay? And it was just a single vertex. That's kind of weird. And that's interesting. A trail is a walk that does not contain a repeated edge. So a trail is a walk that doesn't repeat an edge. Okay, so did we just do that? This one actually, I didn't repeat an edge, so that is also a trail. A path is a trail that does not repeat a vertex. Okay, and a circuit is a closed walk. A circuit is a closed walk, meaning it starts at V and finishes at V, or it starts at W and finishes at W. It's a closed walk with at least one edge and does not contain a repeated edge. With at least one edge and no repeated edges. So for instance, I could go W, E3, C, E5, D, E6, W. That is a circuit. Okay? And a simple circuit does not have any other repeated vertex except the first and the last. Okay, it's a simple circuit. So what I just drew here was a first. This is also what's called a simple circuit. It just doesn't have any repeated vertexes at all. Okay, and so now you're like, well, why do I care about that? Okay. Well, I care about that because when it comes to delivering the mail, doing things like this, any kind of logistics stuff, if you work for UPS, Amazon, any of those, this is where this stuff comes into play. It's kind of a big deal. Okay. So the idea of it being a connected graph, it just means you can walk between them. Okay. So anytime we have an isolated vertex, this guy's isolated, then we would say it's not connected. Okay, it's just not, the graph is not connected. Here it is, now it's a connected graph. Not a big deal. It's not very hard to see. And then if it is connected, then you can obviously connect them with a path. If two of them if vertices V and W are part of a circuit, then and one edge is removed from the circuit, there will still exist a trail between V and G. Okay. I'll look that up in just a minute, show you how that, draw one of those in a minute, show you what it looks like. And if G is connected and G contains a circuit, then an edge of the circuit can be removed without disconnecting G. Okay, so let's look at that. Let's make one that has a circuit here just for fun. Cool. All right. So first of all, it's connected. Sure. Okay. So any two distinct vertices of G, this is the graph G. This is the graph. Any two of them can be connected by a path. Well, duh. Okay. If two of them are part of a circuit in G. Okay. So let's go ahead and label these with E1, E2, E3. So it's just easier to see what we're doing. E5. E6, E7, E8. Okay. So let's put together a circuit, shall we? Okay. A nice circuit. So I'm just going to go C, E3, D, E5, E, E6, B, E2, C. There you go. Cool. It's a nice circuit, right? Okay, and it says this: if you removed one edge, you can still have a trail from V to W. So again, there's any 2 points that are in a circuit. Okay, so let's pick two of them. Let's just say E and B, shall we? Okay, and let's just say we got rid of this guy here. Okay, and let's pretend you didn't even know that guy was there. Oh, shoot. Darn it. Darn it. That's okay. I'll be okay. Now let's just pretend this guy's gone now. You with me? Can I still get from E to B? I sure can. Bloop, 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 bloop. Around there. Yeah, we don't worry about E4 because we're just worried about the edges that we had. Does that make sense? We were worse worried about the edges that we had. Something else that's kind of impressive about a circuit has to do with the idea of a circle. Are you with me? And if you are like me, when you were in your early 20s, you had to go to about 6 million weddings. And, which is fine, it's fine, it's fine, I don't care. Blah, 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 give me the ring, yada, yada, circle, yada, yada, no beginning, no end. And I'm only mocking it because, you memorized the thing. If you look at it as A, C, D, E, B, back to C, okay, it doesn't really matter if you start here and go around to there. Or if you oh, you fiddle faddle. Go away. Go. What are you doing? It doesn't matter if you start at C and go around, or whether you start at B and go around, or E and go around. It's still part of a circuit, yes? So if you make a break, oh, fart. If you make a break at any one point in there, they're still all connected. That's what we're saying by this, okay? They're still all connected. And, and if there's a circuit, which there was, and I get rid of one edge, then the graph is still connecting. Because, in other words, it just went from being a circuit back to a path. Okay? Nice. Now, here are the fun things. Okay. Now, these are the big definitions. An Euler circuit. An Euler circuit. And this is what it means. It's a circuit that contains every vertex and every edge of G. That is, an Euler circuit for G is a sequence of adjacent vertices and edges that has at least one edge and starts and ends at the same vertex, uses every vertex at least once, and uses every edge exactly one time. Okay? So, it would be very similar to if you were picking up the garbage, all right, and you had to go up and down these city streets, okay? I would like to be able to just jump in anywhere and go and not have to worry about backtracking, okay? So, again, when you look at it, I already spilled the beans here for you. If you look at 1, 2, 3, oh no. If I start here, I'm going to have to end at the other odd vertex. So I'm going to fix this. By the way, I'm going to do what is called Eulerizing a graph. And by doing that, what I'm doing is I'm adding edges to make it so that everybody has an even vertex. Okay? Now, when you are delivering the mail, you have to go up and down both sides of the street typically. Okay? So that means every street, it's more like every side of the street is an edge in itself. Same with picking up the trash. Usually you go down one side of the street, turn around, come back down the other side. Doing street sweeping, similar procedure. Okay, you go down one side, turn and come back up the other side. Each street, in essence, becomes a street in and of itself. I suppose if someone lived at the far end of a cul-de-sac, or a dead-end road, I guess you just drive out there, drop off the mail, and come back, and there was the only person on that road. Technically, you're deadheading, but what are you going to do? Okay, in essence, you've made going down the road. One guy lives down there, and the rest of the town is down here. You go down the road, and you technically you come back down. You can't just get down there and go, well, I'm stopping, not going back home. That's ludicrous, okay? So, in essence, you Eulerized the graph. Now, what I want to see by this here is, check it out. What we want to do is we want to start, let's say we want to start here. I'm going to start A and finish at A. But I'm going to label them 1, 2, 3, 4, 5, 6, 7, 8. Notice it's possible. It doesn't always mean it's easy to find it. I almost went back up here. I would have been screwed if I'd done that. You with me? I had a variety of ways to go, but as time goes on, there's fewer and fewer options. So in other words, to do an Euler circuit, there has to be all vertices have to be even. Okay, so that Konigsberg bridge problem, what they were asking for is there an Euler circuit? The answer is no, there's not, because they were all odd vertices. And even two odd vertices, again, they can't come in by ones, they come in pairs. Even two odds, you can't do it, okay? And so that's just how that's a very easy problem to look at. And again, in the real world, what you often do is you'll often add in an edge, if you will, and you'll call that Eulerizing the graph. Okay, something that I like to do from time to time, and I'll probably do this with you guys as well. Make a worksheet for you. It looks kind of like this, but let's see here. Oh goodness sakes! What's the name of that stupid town? Come on, Jay, you're better than this. No, you're really not. All right, so Biggs Junction, but I don't want Biggs Junction. That's not what I was looking for. Go south, dummy, go south. Yeah, Wasco's a little bigger than I wanted. No, there's a little town out in the middle of nowhere. Oh, what is the name of it? For God's sakes. I'm losing my marbles. Oh, I'm going the wrong way. Condon's also very small. That's not the town I was looking for. Grass Valley is also small. That's not the one I was looking for. Shaniko, there it is. Ha-ha! Shaniko, in essence, a little ghost town of a place. There it is. Nice. So a person could talk about delivering the mail if you were the mail carrier in town. Okay? If you were to slap these things on there, the little picture on here like so, and zoom in a skosh, you're like, you know, there are streets in this town that you, as a postman, don't need to go down. Okay? That's a barn, dude. You do not need to go down this piece of town. Does that make sense? If you're the postman, yeah. Like you might just make the loop over to here and back over to here, but then as you can see, like there's what are you gonna do? I guess you can make the loop down around here and then back around. The idea being is that you don't need every edge in a small town for delivering the mail. Delivering the mail is something entirely different than sweeping the streets. If I'm sweeping the streets, I got to go down both sides of every one of these streets. Every one of these streets between these intersections would be 2 edges, right? That's not necessarily true for delivering the mail in this tiny town, because you just have to go down this side of the street, delivering mail here and here, I guess, but not on this side of the street because no one lives there. Make sense? So think about that as we're doing this. So there's 2 different kinds of graphs. Okay, there's going to be the graph where I have to go to every house, and there's the graph where I have to go up and down every street. They're 2 different things. Okay, and so Euler's says I have to. It's all about the journey, if you will. Okay, and so street sweeping comes to mind. Street sweeping comes to mind. The meter reader person that reads your gas or the water or whatever, the meter reader, they have to go up and down every street on both sides of the street. I mean, that's just kind of the things that they do. Street sweepers, garbage men typically. Okay, but different would be like the UPS, maybe mail, maybe not as much mail, but not always. But UPS for sure, FedEx, okay, those kind of guys. Well, what they do is it's all about the destination. This is all about the journey, if you will, the edges. It's all about the edges. This kind of deal is all about the vertexes. And the vertices in this case, vertices. And the vertices in this case wouldn't be the intersections. The vertices would be the houses, all right? Or for me, running errands, I typically don't care about going up and down every street in the neighborhood, for crying out loud. That's just dumb. I need to pick a street and then get to, Safeway, and then I got to get to somewhere else, and I got to get, wherever. I was going to say get my dry clean, but I haven't been to dry cleaners in years. And so there's another kind of circuit that we'll look at, and that's what's called a Hamiltonian circuit, and it's all about the vertices. Okay, so Hamiltonian circuit, you must hit each vertex. You hit each vertex. Learn how to spell, you jerk. Hit each vertex. Okay. That is the Hamiltonian circuit, a sequence of adjacent vertices and distinct edges in which every vertex of G appears exactly once, except for the first and last, which are the same. Okay? So a Hamiltonian circuit is a simple circuit that includes every vertex of G. Okay? It includes every vertex of G. Okay? And so here's the game. It's a pretty straightforward deal. Okay, hit every vertex on exactly once, except the one you started on. Okay. Now, the thing to remember about Hamiltonians is that it's a simple circuit. And again, let's just review our memory for the actual definition. A simple circuit is a circuit that does not have any repeated vertex except for the first and the last. Okay. A circuit is a closed walk that contains at least one edge and does not contain a repeated edge. Okay. So remember, the fact that it is a circuit, you're not repeating edges. Okay. And you use each vertex exactly one time. That's what makes it a Hamiltonian circuit. Okay. Now, as I say, this one here is all about, for me, about running errands, going places. Okay. So if I have these places to go to, typically in town, there's about 100 ways I can go to anywhere. If time is not a factor, Saturday morning, you're not in any ginormous hurry to get your shopping done. It's just something that's got to get done, but you're not like in any grand hurry. I guess a person could go from anywhere to anywhere just fine. So we'll have your house, Safeway. I'm not sure why you're going there. Don't care. The cleaners, sure. Chuck E. Cheese. That's kind of a dumb thing. I'm not going to do Chuck E. Cheese because you'd probably have to go there at some point. FedEx, place, drop something off. Somewhere else boring. The bookstore. I wouldn't like say coffee because you're like, I got to get that first. Nah, whatever. I hear you. If you think about it, if time is not a factor, in other words, if it's not like it's 100 degrees out today, I gotta get ice cream, I gotta take the kids to school, and I gotta do this, and take the dog to the veterinarian, I gotta do this and that and the other. I'm gonna get ice cream first because it's closest to my house. You're an idiot. Okay, I'm sorry, you're an idiot. No one's gonna get ice cream first. That's just stupid. Even on a cold day, I'm not getting ice cream first. That's just dumb. Likewise, if time matters, and it usually does, going to work because it's closer and then dropping the kids off after work, it just seems goofy. So typically you're going to drop the kids off, even though it may be out of your way. It may be kind of annoyingly inconvenient to get over there to drop them off to come back to your work. Sorry, that's not how it works in the real world. But if this is a situation where I got things to do, I'm planning my delivery route for the day, what have you, there's no pressing this has to get done before that kind of a deal, then yeah, I'm just going to go here, I'm going to go there, whatever it happens to be. So what's gonna cause me to make a decision is typically the time or the distance between these places. So in a big city, it's typically not distance so much as it's time, as you well know. Okay, and this one here is like 33 or something, whatever. Okay, it doesn't take a rocket surgeon to see that we're probably not going to go from the bookstore to Safeway. It's like probably getting on. It's like getting on Highway 26 or something. Like, why would you get on that mess if you didn't have to, kind of a thing. Okay. This one here looks like a long distance from the bookstore to the cleaners, and it might be a long distance, but it might be a really easy, path to get between those two things. So clearly, in a Hamiltonian case, there's going to be the idea of always minimizing time or distance, whichever it happens to be. And the idea is that there's going to be better or worse ways to get there between here and there, okay? And so I'm going to kind of show you, just kind of tip my hat to it a little bit, and we'll do some more with it later in this chapter. Or we'll actually do an assignment with it a little bit. But it's kind of easy to do, but it's not a really hard problem to look at, but it's just think about this a little bit in terms of what would be the best way to go. Okay? And so if you start at the bookstore, well, the closest place to the bookstore, I guess, would be the cleaners. Right? And then from the cleaners, the closest place is FedEx. And then from FedEx, well, you have, oh, shoot, darn it. You got to get back up to there. Ding dong. You can go to Safeway or you can go to your house. Well, let's go to Safeway, I guess. Safeway. And then back to your house. Okay, well, the way I do it is I go, and then I got to get back to the bookstore. Otherwise, it isn't really a circuit, is it now? Now, before you get all weirded out by this, let me finish. 7. 40 to 49 as the total distance there. Remember, they are circuits. It doesn't matter where I start. It matters that everything's on my list as I go around. I could have also started the cleaners. Clearly, I'm going to FedEx from the cleaners. I mean, that's obvious. That path, the 2-1, is going to be on every single one of these. Guaranteed. Guaranteed. It's going to show up on every single one of them. From FedEx, the closest place is Safeway again. And from Safeway, the closest place is, well, I go back to the cleaners. Oh, I can't go back to the cleaners because that would be completing the loop, and I don't want to complete the loop yet. I need to get over, well, I got to go to the house or the bookstore. Well, house, I guess. So 20. And then from the house, bookstore is 10. That's pretty cool. And then I got to get back from the bookstore back to the cleaners. And what is that? That's 7. Hey, wait. That's the exact same path. If you can see it, it's house, bookstore, cleaners, FedEx, Safeway, your house. Here it is. House, bookstore, cleaners, FedEx, Safeway, your house. They're the same. Will they always be? No. Not always. Let's continue, shall we? You could also start at Safeway. If you go to start at Safeway, then you're going to Cleaners next. Oh, cool. And if you're going to Cleaners, the next closest place would be FedEx, of course. As I say, that one's going to show up on every one of them, I think. And then you're like, oh, cool, I'll take this 10 back here. No, you're not taking that back there, dude. That'll take you back to where you started from. You don't want to go there yet. I'm going to go to the bookstore for 13. Cool. Where haven't I been yet? Well, I haven't been to the house yet, and I've already been to the Cleaners. I haven't been to the house. So I got to go back to the house, which is 10. And now I got to get back to the Cleaners, or back to Safeway, rather. Safeway, which is 20. 30, 43, 45, 50. Ooh, that's not that far off. All right, let's start the house this time. House. Closest place to the house looks like to be the bookstore. From the bookstore, the closest place is FedEx. This is looking very familiar. Once you're at the books, the FedEx, here's not the FedEx, you ding dong. The Cleaners, I mean. Sorry, the Cleaners. And then FedEx. And then from FedEx to Safeway, I bet. And then from Safeway back to your house. Oh, what? It's 49 again. Nice. The only one I haven't started at so far is 1, 2, 3, 4, 5 of them. It's FedEx. FedEx to the Cleaners. Nice. From the Cleaners, the closest place is Safeway. From Safeway, the closest place is back to FedEx. So can't do that. So back to your house for 20. To the bookstore for 10. Back to FedEx for 13. That's 23, 43, 48. That's 50. Hey, that's the same one we did up here. Sometimes there'll be multiples of the same. Sometimes they'll all be the same. Sometimes there'll be quite a few that are different. But any of these ones are here. They're the exact same. And would it make any difference if I went home, Safeway, FedEx, Cleaners, bookstore, home? That wouldn't make any difference. Which direction I go, the distance is the same. What I just showed you right there is what we often use in our daily lives, the nearest neighbor algorithm. Algorithm, just a big fancy word for mathematical recipe. It's an idea. It's a thought process. The nearest neighbor algorithm just says I'm going to go to the next nearest place, the next nearest place, and so on. Notice that had you done it that way, what a guy could do is, this is clearly the short, this guy right here, which is the same as the other two, that is the shortest route. So you could have done them in one order or turn around and go the other order, okay? And that's fine. And work your way backwards, in other words. So clearly going to the bookstore is the closest place from your house. From your house, in this circuit, the furthest place to go is to Safeway. And you could have gone that way and just worked your way back around, okay? Some of us in our daily lives like to get the closest stuff out of the way first. Some of us prefer it, if you will, to, if you want to think of your route as linear, okay? Sometimes I like to think of my route as linear. When I grew up out in the sticks, way out in the country, it was linear. I mean, boom, 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 or whatever. Okay, I would just drive straight to there and then just turn around and come back, whatever. I mean, that was my loop. Or I could have gone this way and then come back. It wouldn't have mattered because, I had a 10-mile drive to town, to the closest town. The 3 or 4 things I need to do are primarily on the main drag, boom, 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 and then turn around and come home. Which one do you want to go to first? I don't know. I wouldn't do the one in the middle of town, then come back to the closest one, then go to the farthest one. That's just stupid. I'd probably hit the ones maybe that are, I don't know. It just depends. And again, typically, this is in the absence of time. So if I had to get something to the post office and it was 4 o'clock, 4:30 or whatever, I'm obviously going to the post office first. And then after that, there's some of the other places like the grocery store and whatever. They were open after 5 with no real hurry to get to them. Okay. And so in this situation, it's a pretty straightforward way of looking at it. Now, I'll be putting up a quiz this week. In that quiz, you'll be doing an example out of a different book I have, if I can find it. And it talks about this book. This Hamiltonian one is also known as what's referred to as the traveling salesman problem. And obviously the traveling salesman's got to cover a lot of ground. You don't want to be backtracking, okay? But you got to go to this business, and this business, or this home, and this home. I can't be backtracking all the time. I can't be wasting time. I want to just continue to move in a circuit, and then at the end of the day, I want to get home. Okay. Again, in my mind, if you were the traveling salesman that started, I don't know, your route was in Portland, and your route was to go out to, Pendleton and back every day. Pendleton, that's a long trip every day. But there you are, and then back. Do you go run all the way out to Pendleton and start your deliveries and deliver all the way back? I doubt it. My guess is you deliver on the way out, and when you get to Pendleton, you're done. Scoot straight home. I don't know. I didn't make up the thing. I'm just saying maybe that's what your route is. But my guess is you don't go to the Dalles, turn around and come back to Hood River, then go out to Biggs, and then turn around and come back. No, it's ludicrous. So the idea is you're trying to minimize the thing. Now, it's harder to visualize in a straight line in some respects. I mean, it's literally down and back. Okay? But what if you had deliveries kind of across the state of Oregon? And you're like, well, across the state of Oregon like this, I mean, yes, you could come clear down to Burns and then back around. One would think that one would, I don't know, or some similar, it's going to end up looking like that when it's all said and done. Because once you're in Burns, well, I guess the next closest place, as I'm kind of I've already been to Bend. So like the next closest place of any, size or import that I need to go to maybe is Baker City. Well, then cut up to Baker City. Oh, now I need to go to Pendleton. Well, isn't that convenient? Come back up to Pendleton and on back around. Okay? So most of these take care of themselves pretty easily in a big scenario like that. You don't even really need to do any math. The only question is, do you want to go this way first or do you want to go this way first? Okay? There's not a lot of thought process to that. Okay? In town, it's a little different. And again, in town, it's not mileage. Clearly, this is all mileage. This is all about mileage in the state of Oregon. I mean, you're all over the place. So clearly, I'm going to go to the next closest place, and it's going to be about mileage. It's 60 miles versus 400 miles. Of course, I'm going to go to the 60-mile one next. In town, it's often, I'm going to do this one here, where you're like, well, it's further. Yes, it's further, but I can get there a lot quicker, and I don't have to sit in traffic and screw around or whatever. So I'm going to go over there, and once I'm there, then it's going to be closer to this one over here. And you're like, well, I'm putting more miles on the car. I am, but I'm not wasting as much time. So again, frequently time in the cities be more important than mileage. In the big macro sense of the things, obviously mileage is going to be more important. Okay, so that should take care of 10.1 and 10.2. We'll be doing some matrix representations of these as well. They're called adjacency matrices. They're kind of fun to mess with. So we'll do that next week or later this week, I guess.